Hello. Hello. Can you hear me? Okay. Well, hopefully you can hear us, hear me. So let me get started. So welcome. This is Junichiro Horikawa. This is a live stream for tutorial for Houdini. And yeah, I've been doing this weekly now. And each week I'm having a different topic for creating some algorithmic design related stuff using Houdini. And today the topic that I would like to go for is to create a so-called TSP art or TSP path generations. TSP stands for traveling salesman problem, which is to solve a problem how salesman can go around each cities in the world without going to the same city twice in a shortest distance. Okay, and as a result of solving a TSP, a travel salesman problem, you'll be able to get some kind of a path like this by going through each points just once. Now this is a point that I have initially, and by just going through each point once, creating the shortest path will get you to give you a path like this as a result. And by solving the TSP, you'll get a path like this. And there are the TSP art. The name TSP art comes from one of the website that I searched, and I'm just using it the same name, which explains about how it looks, how you create it. Now initially, if I look at when I was browsing this website, it does show you how it should look like, how the TSP can be used to create an art like this. It does say how you can make it in this page, and it says you need to use some kind of heuristic solver in order to solve the path. And seems like using these heuristic solver is not done in real time, but has to use some kind of a pre-made solver, which I didn't really want to use it. So I was looking for a way to make it more or less real time using a simple algorithm rather than using a solver like these. Okay, so what I came up with is to use a simple algorithm for solving a travel salesman problem called two-opt algorithm, or two-opt ways, which is this. If you go to the Wikipedia searching for two-opt, it shows how you can solve, how you can get a shortest path out of the current existing network by changing some of the paths, switching some of the paths to avoid crossing. Now the conclusion here is that if you want to get the shortest path as much as possible in given network and given connection with each of the points, to avoid crossing is the way to do it. If you try avoiding crossing like these, then in the end you'll get the shortest path by avoiding the crossing. So that this is how you explain, this algorithm explains you how you could avoid having these crossings. Okay. So I'll briefly explain what this two-opt algorithm works, which is pretty simple. If you have a curve like this, a simple path like this initially, and you want to make it to a curve like this so that you don't get the crossings, now solving like this will give you also a shortest path as well. Now, in order to solve it, first you pick a randomly two path, which is not on the neighbor edges. So you pick two edges, one could be this one, and since you want to avoid the next edge to be the neighbors, so you don't took this one but instead take this one. And what you do is first of all name it to A, B, C, D. Then first you calculate the lengths between CD and AB as a initial length. Okay, then what you do is to switch the path from A, reconnect the path, so from AB to AC, and CD to DB. Okay, so swapping B and C to create a path between A, C, and B, D. Okay, and the next thing you want to do is to calculate the lengths by after swapping the connection. Then if the first initial curve is larger than the second one, which means by swapping the points, the connection, you'll have shorter path, which gives you a better result in the end, and could be solving the problem of the crossing. So whenever you found the shortest path, you choose that one. So in the end you get A, C, B, D, and continue doing this until you have no shorter path available, even if you swap at any place. And you also want to rename this to A, B, C, D again, so that for the next step you could again look for use the same order to look for the other connections. So this is about it. I mean, this is just a simple examples, but it could also even work for any kind of like a complex connections. You just need to pick randomly two edges and swap the connections, swap the one of the connections to each other, and recalculate the edge lengths. Then if the lengths calculate the total length of the curve, and if the total length of the curve is smaller than the previous one, then just use that one for the next step. Okay, so let's try this on, and I will try to do this in Houdini, just like every time, just like all the other videos. Now as a result, you'll get something like this. So initially you need to create a initial curve like these, I mean, it could be more dirtier or it could be more cleaner, but initial state is pretty important for this 2-opt algorithm, because if it's too dirty, if you have too many crossings, you have to have so many places to solve, which gives you longer time to solve the holes connections. But if you have less and less connections in as an initial state, it will be more quicker to solve. And I'll give you some tips how you can make the initial state to be a bit less complex than usual. So let's say this is the initial state. You could solve the problem like these by continuously solve the crossings using solver, using the 2-opt solving algorithms. Okay, so let's try. And thank you for the comments. So, other comments, why don't you make in-depth course of procedural modeling, like modeling bridge build? If anybody's interested, maybe. I don't know if that's something people want to hear from me. I'm not sure. And we'll be continue of algorithmic design playlist. You mean a Vex course, I guess? I do want to continue doing the Vex course as well. Which I have left in some time, several years ago, like 2 years ago, I guess. The last time I did was maybe a matrix or something. Maybe I could continue doing it with some, I guess there are still some basics left to talk about the Vex. Or maybe going for Python could be interesting as well. Not sure. Well, anyway, let me think about that. And let's start implementing this 2-opt algorithm for solving the crossings. Now let's first of all create some geometry node as always, and try to create some simple situations for crossings. I'm just gonna create a curve polygon, and try to create some simple situations just like I did on the sketch. I'll just create 4 points like this and try to solve this first. Then I'll continue developing the algorithm so that can also be used in more complex curves. Okay, so let's do that. Now, in order to do that, I am first of all going to, well, since I have to do this recursively, look for the edges which could be used to swap and make the whole curve shorter. So I don't think point wrangle or primitive wrangle will work for this purpose. I'll just go with a detail wrangle to create the algorithms. I don't think it's possible to do this in parallel. I think what I have to do is to look for the first curve and look for the pair, another curve for the pair, and compare these two curves by swapping the connections. Then if the length is not changing, then look for other pair and so on. So you have to do a double loop for each edges if you couldn't find any best solutions. So it might take time if you have tons of edges, I think. So that's one of the reasons why you want to optimize the initial state. to be able to solve it in real time. Okay, so but this one is pretty short. You just have 3 edges, so it's pretty easy. It should be easy to solve. Now, one thing I would like to do first is to create a loop through the points, and in this case I want to loop, so we have 4 points, but I just want to loop 2 times because what you need to do is to take 2 edges as a pair. So the first loop that I'm going to create is something like this. So let's say 0, 1 is the first edge and 1, 2 is the second edge. So that's the that's the whole first edge that you want to loop for, and you're going to skip the 2 and 3 for the for the first loop, because by the end when it comes to 2 and 3 2 and 3 edge, you're not going to have any other pairs because it's already been chosen by the previous loop. So so this is the first loop that you want to create, and since you need to create a pair, you want to have another loop. So let's call this J, and let's call this I plus 2. So when you choose 0, 1, the first edge to be, what happened? So if you want the first edge 0, 1 to be the first edge, then the next edge that could be pair, it cannot be a neighbor, but could be a 2 to 3. So you always want to make the minimum number for the next edge point, next starting point for the edge to be I plus 2. Okay. Then and this will be -1 for the final, since you also need the endpoint number. Endpoint number will be a endpoints -1. And so these are the 2 loops I mean the double loop you want to create in order to go through all the pairs from one curve, one polyline. Now, before going into the code, I might also want to convert this polyline, which is one continuous polyline, into a bunch of edges so that I can swap it inside the code. Right now, if you try to swap it, using the current polyline, it will mess up the order, so because the edge is connected. So what I would like to do is to convert it into a line so that each edge will be separated, even though the point number is not increasing, the edge is separated, so it will be more easier to swap. Okay. Now let's go back, and I think I have some error here. What's up? Reference to undefined variable int. Huh. That's funny. Oh, okay. Forgot to say int I. Okay. Alright, then let's try to get a b c d as a point. So vector A. So I'm gonna use A as a position for the point A, which will be at I position. So that's the first curve starting point, and the first edge, the end point, will be I plus 1. So in this case, 0 is A and 1 is B, okay, creating one edge. Next, let's create a C. In this case, pick J. So J is I plus 1 and initial iterations on the loop. So in this case will be, if I is equal to 0, that will be 0, 1, 2. 2 is C. And J plus 1 will be D, which in this case the last point. So even though this is a loop, since I only have 3 edges, this loop only runs just once. Okay, what's happened? What happened? Okay, something messed up. What's happening here? So J plus 1 for the D. Okay. Now let's next thing I would like to do. Now I'm having some error here. E9 seems like I'm getting some weird error. Might be having some problems. Okay, what's this? Oof. That was weird. Okay, so I have A, B, C, D as a positions. Now next thing I would like to do is to calculate the current edge lengths, okay, between A, B and C, D. So current length is B minus A dot lengths plus D minus C lengths. Okay, so this is the current distance for edge AB and edge CD. In this case, a length 1. Now, next, what I want to do is to try to swap the positions. So in this case, I want to calculate the distance between AC and BD. So let's also do that. Just calculating the lengths. Lengths between what was it? CA, AC, and DB. And what I want to do is to compare these two. This is the new one after swapping. This is the current one before swapping. And if the new length is less than C length, then that means by swapping the point with with C to B and B to C, you'll be able to get a smaller distance for the whole curve. So in that case, you actually want to physically swap the curve positions. So and what you need to be careful of is the order when you do the swapping. So let me go back to the sketch, and if you have curve like this, and if the order is like this, 1 2 0 1 2 3, and if you want to make it a curve like this, and that will become 1 2 1 0 1 2 3, I guess. Okay, and maybe this is a bit hard to understand, so let's give another let's give another point like this. So in this case 0 1 2 3 4, and probably the optimized path is something like this. So in this case the order should be somewhere like here. So as you can see, if you look at this part where it's been changed, the order has been changed on the reverse directions. So previously it was going this way, but then the new path will going this way, the other way. So whenever you swap the point from 1 to 3, you always need to make the order of the current curve in between 1 and 3 reversed, going to the other directions from the previous one, so that it can connect with the current one, current 0 1 and 3 4 in order. Okay, so whenever you do swap, do the reverse order. That's the rule. So in this case, what you want to do is to loop in between, create a new loop from, let's say, int n equals to I plus 1. In this case, it's if we are talking about 0 for the I, it's 1. In this case, I plus 1 is equal to 1, and until n is j plus 1, meaning in this case the j, if we're talking about the initial iterations for the loop, I plus 1 is 2, j is I plus j is equal to 2 as a minimum, and then j plus 1 is 3, so this is the end. J plus 1 in this case means 3, and you don't want to go over that value, so 2 is the end of the loop. So meaning what you actually doing here as a loop is going between 1 to 2, just in between the edge that you just picked, edge that you have picked inside this loop, inside this double loop, and increment n by 1. Now within this loop, what you just want to do is to make the order of this curve on the other direction. So if it's saying 1 2 from bottom to top, then you just want to make it go from bottom to top. Make the top part to be 1 and the bottom point to be 2, second position. Now to do that, pick the point position and which is j minus well, actually I also want to have some count informations, so let's create some value called count, which will be incremented by 1 inside this loop, and then gonna go j minus count. Okay, so this will be, if this is starting from 2, then this will become 2, 1, and 0 by doing the loop. So starting from the end of the loop, starting from 2, then in the next phase going to 1, meaning you're just getting the end point positions of the polyline in between these two edges, then counting up from the end so that you could do the reverse ordering. Then once you get that positions, set that point to set that point position to a current to the actual order, actual reversed order. So I'm just this is kind of actually swapping. This part is actually doing the swapping part. So as a result, you'll be able to just reorder the curve in between these two edges into the reverse order, and that should still work even if the curve becomes more complex. So let's try having other curve, try to make it a bit more complex. So currently you still have 1 crossings, but the number of points has been increased. Let's see what will happen with this one. And we're getting a solve. And you can see that the order has been changed, and maybe there seems to be a bit of problem here because it's kind of ignoring these points that existed. So maybe I think I need to also prevent something, prevent the existing point not to disappear as well. So what I'm doing wrong here is that once you found the solutions, as soon as possible, as soon as you found the best solutions for this step, you just want to cancel all the rest of the optimizations, because this cannot be done because after you found the first edge, in order to optimize it, you kind of need to recalculate the correct edge lengths and so on. So right after you have found the optimal swap position, swapping the edge, what you might want to do is to do a exiting the current code like this. And in order to but this will only solve 1 crossing or 1 shortest path, making just 1 edge optimized. So what you need to do is to continue doing the same step over and over again until you have the best result. So meaning what you actually need to do is to use the same code in a feedback loop over and over again until you get the best result. So fetch feedback, fetch feedback. So this is the initial state. In the first loop you get the result like this, and the second loop you get result like this, and seems like this is the best solutions. So by continue doing this, you should be able to get a shortest path for the for the whole path. Now let's try to make it a bit more complex, see if it's still gonna work. Let's see. Holy curve. say I have more complex, which has tons of crossings like these. Doesn't have to be closed curve, but things like this. Now let's see if it could still be solved. So initially this was the result, and by raising the number of loop, it does seem to start solving. And if you continue raising up the iterations for the loop, in the end you have no crossings, meaning you got the result with the shortest path as much as possible in this array of points. Okay, so this is how the 2-opt algorithm works. You just need to optimize the lengths of the edges one by one with the loop. I mean, I do think there is a way to do this in multi-threaded way without solving the edge like one by one. But the brute force way is to do something like this, and I'll show you by optimizing the initial state. You could make it a bit more faster to apply some multi-thread options using like primitive wrangles or point wrangle. So I'll show you that later, but for now let's try to remember this process, okay, as a basics. Right, so well, I got the comment from Alan, the left sections isn't the shortest path, I think. I guess this is the part you're talking about. Things with this is that the first point, the first and end point is fixed, because this is not a closed curve. Or is it? It's not actually. Yeah, it's fixed. So you always have to have the first point and end point to be at this point with this implementation. So using those points, starting points and end points as constraints, you need to find the shortest path which connects all the points in one path. So that's kind of a constraint. If you could change the starting point and end point, then there's a chance that you could have more optimized paths. Okay, so that gives you one question: if it's possible to close the curve in one and make it as a looped curve, which might give you a better result in the end, which you could also do that. So let's see how we could do that. Now that will need additional like calculations, because you also need to pick the curve, pick the looped curve path in the end. So let's think how we could do that. Now let's go back to this curve and try to make it a closed curve by, can I do it here? Not sure if I could do it here. I'll just give a primitive properties. Go into the face halt tab and make it close straight. Okay. Now it's a bit hard to see here, but after connecting the convert line, it will look like this. Okay, so let's see what would happen using the same code to solve this. Now, seems like we have some somewhere which hasn't optimized much. which is somewhere around here, which is somewhere close to the start point. So we might need to look into that. Okay, so because we're writing something like this, there are some points we're skipping for the as a candidate for the swapping. So if the curve is closed, we do need to think about the situations if the curve is closed or not, so that every candidate and every point can be chosen as a candidate for a swap. So to solve that, what I need to do is to change these conditions where where constraints the number of points to look for. Okay, so let me think what will be the how we could solve that. Okay, so let me first check the comment. So I've written notes for each lesson, but I can't freely apply this knowledge in my projects yet because I lack deep understanding. Deep understanding come to you. When did deep understanding come to you? It's a hard question. Well, practice makes you a deep understanding, I guess. Even if you do the basic or simple like processes, even writing a simple code like these will make you understand little by little if you keep doing it, I think. And we're kindly requesting you to teach architectural projects like building bridges and roads using VFX project-wise. Very useful. Okay, sounds like interesting idea. Let me try that in the future. Okay, so where was I? So let's try to solve this. So so what I need to make sure is that every point is going to be picked. Every edges can be picked for the candidate, and let's check the number of edges we have here. Okay, and let's try with a bit more simpler situations like these. Okay, so so one thing I need to be careful is that 0 could be a candidate between 0 and edge 0 cannot be candidate with that cannot be paired with 1 or 7 if it's closed. So if I look at this code, if that's what's happening, actually, first of all, I think I can make this value to be equal to 1 in this case. Let me check. Well, not sure. Let's see. Yeah, I think this could be increased like 1. So that means if I is equal to 0, then it can go until, well, maybe not, or maybe yes. Yeah, since it can be looped, so it could go till here. So I think this is okay if it's looped. And then for this, if it's I plus 2, which is okay, which means starts from 2, and then till end point 0. Could go till here, I guess. Could go until here, I guess. So in this case, now the problem is if it goes above endpoints, then it's not really looping, because after endpoints -1 it becomes 0 and starts incrementing by 1 again from 0, 1, 2, 3. So maybe what I would do here is to create a start replace these conditions with a variable like these. First of all, okay, and what I would like to try out is make sure that the starting point will start maybe from -1 of the current point number, and for the endpoint it's incremented by 1. So if it's 0, if endpoint number is 0, let's start by 7. In this case, this will be negative. No, actually not. It's not actually a negative. Wait, I think I'm doing wrong here. This is fine. Wait, let's rewrite it. So let's say end is endpoints 0 minus 2, or just say endpoints, and we'll replace it like this. End minus 2 is the end, and end minus 1 is the end for the second loop. Okay. Now, what I want to do is to change the starting value, this 0 part. So initially, when the curve was opened, I was setting this to 0. Okay. But if it's closed, this could be negative value, which then could be calculated with a modulus, which in this case becomes 7. But I'll do this later, not here. Just gives you some ideas that I want to start the counting from here for 7 in this case. And for the end, I might want to stop by endpoints plus 1. So in this case, endpoints is equal to 8 because we have 8 points. So number 8 doesn't really exist already, but it should be somewhere around here next to 7. And also by adding 1 to it, the actual end point number will be somewhere around here, 1. So this is the starting point, this is the end point, which has some which has 701 as a intersected value. So it does have some intersections. It should cover all the edge that I want to calculate, or I want to include as a pair. So that's kind of a reason why I did something like this. Now, when I'm trying to get the point position for A, B, and C, A, B, C, and D, I have to make sure that I plus 1, J of J plus 1 is within 0 to 7. So this is where I need to make sure that the point is within the point number. So to make sure, what you could do is to add a number of points to each of the I and J and calculate the modulus. Calculate the remains by dividing by endpoints. So if it's just 1, you get 1 as a result, but if it's -1, then you should be able to get the value 7 by calculating like this. So do the same for all the other stuff. In this case, I plus 1, J plus 1. Okay. Now, this should give you the right value for A, B, and C, D, and do the same calculations to calculate the lengths. And you also need to be careful about these values as well. This could be negative, so do the same thing. Add it by endpoints. Calculate with modulus. And do the same thing for this n as well. Could be negative, or more than n points. So make sure it's always stays within the amount of n from 0 to n points. Now there I have some. So let's check if I'm doing the right calculations here. Hopefully it is. Now let's check the result. So by increasing the amount of, okay, so seems like I'm doing something wrong here. Nothing is changing. So let's see what am I doing wrong here. So starting from -1, endpoints plus 1. Okay. And I plus 1. Am I doing this correct? Yeah, I think. And am I doing this correct? Endpoints. So J minus count plus endpoints divided by. Okay. Let me check when I make this to 0 and this is also 0, which should be the previous conditions. Okay, so this one works. So maybe I'm doing something wrong here. Okay. So I might be doing something wrong here. So start, if I do this -1, does it? Yeah, it does run. Okay, just seem to run. Now when I add this and plus 1, now it starts to fail. So what if I do this to 0? Okay, still works. Maybe because it's intersecting the curve, intersecting two edges, that might be the problem with this one. So if it's closed curve, I might not need to add plus 1 to this one. And make sure this is -1. So this is the previous condition. Doesn't really seem to change anything because it's not that complex enough. So if I take a look at this one and go till the end. So this is when I was having a start equal to -1. When I make this 0, I got this result. So let's see, let's calculate the lengths. So shorter is better, right? So hopefully by introducing -1 for the start gives you a better result. So throughout. So this is a previous implementation which gives you a length perimeter total perimeter is 8.22, and if I make the start to -1, hopefully it loops and makes you a better result, and yeah, give you a slightly smaller result. So this might be the shortest path for this solution. So hopefully it made sense to you, how this will give you the result. I wasn't really sure why this did not work, but maybe that's because by adding +1 you're going to get a intersected edge which is interfering with the calculation or the comparison created here. So that might be the reason. So let's just give start -1 for the loop if the curve is looped. But I guess the problem is, again, is that if it's an open curve, then you always want to make sure that the start is 0. If I make this opened, I don't think it's gonna work. I mean, it is working, but I think it will again interfere at some point. So let's check if the curve is closed or not. Although this is already splitted, so can't really tell if it's closed or not. So what I want to do is to connect the original curve and retrieve the information whether it is closed or not by checking the intrinsic data called closed. So prim intrinsic closed. We have only one curve, so if it's closed, let's just set the start by 0, and if the closed value is equal to 1, then update the start to -1. Or you could either make the end +1. Either way is fine. Okay, so that should automatically solve the problem. So if it's not closed, then should be using the open curve solution, If it's closed, it should use the closed curve solutions. Okay, well, hopefully that's gonna solve problem. Now that we have the base, we just need to implement this for a longer path, just like we did on the OptArt or this website. So first we going to create some point cloud based on maybe some image or randomly created points, then try to create some optimized path like this using the code that I have just shown you. Okay. Hi Shivarathli Amish, thank you for the super chat. Thanks for considering. Hoping you'll start soon, even if not free, an affordable price. Be great project-based learning, builds, industry skills. Okay, well, yeah. Please hold on. I'll try to create something. Yes. Well, maybe I could start by creating a building. Maybe. I do have some experience creating a building in Houdini for some projects, so even from map based, so maybe I can share that kind of knowledge sometime. Alright, so let's name this to opt. Okay, so now that I have these information, now that I have this code, let's start creating a point cloud. So what I'm going to do, just going to import the texture, then create the point cloud from that texture. So I'm going to use a copnet. Inside the copnet, I'm going to use a file and import some image, which you want to use to plot plot the points to. Just going to import this skull image that I downloaded from a stock photo website, which is not free to like redistribute, so I'm not going to include this on the final projects. You can just download any of your own image you want to use. Now I just want to have a contrast from this image so that I can use it to distribute as a density. So I'm going to use a mono node to convert it into a monochrome image. Okay. And then go outside the copnet, try to make it on the XZ plane to create some points on it. So let's do that. I'll just create a transform node, rotate it to 90 degrees. Okay, maybe minus 90 degrees. Right. Then let's give this a bit of scale, like 5 times bigger. Doesn't really matter about the scale, but just to make sure that the points, the distance between the points is big enough. If it's too small, it might give you some problem issues. So in order to make sure that the space between the points is big enough, I'm going to scale this image a little bit up. Now, in order to scatter the point based on those contrast, what I am going to do is to create a grid which covers these plane with these image. First of all, make the rows and columns 2 by 2 and use the match size to control the position and the size of the grid to match with the image. So scale, uncheck the uniform scale so that the size of the grid will match with the picture, the image. Then do some remeshing to this grid so that I can apply some contrast information to each of the point on this remeshed grid. Smaller the triangles, the better, because you have more detailed value you could apply in each point. I guess this is fine. Now using the point wrangle to copy the contrast or sample the contrast information from the cop image to each of the point. So, and since this cop image is actually a volume, if you look at it, this is actually a volume. You could use a volume sample to kind of sample the image value. In this case, as a contrast value, black and white monochrome value, which is in between 0 to 1, I think. So for each point on the remesh geometry, you could use volume sample to get the density value, I guess. I don't really know the name. I mean, this volume doesn't have any name, says no name, so I'm just gonna choose the volume number, then use the current point positions to sample the value, which should be a contrast value. Let's check that out. Copy that value to a color, then yeah, I think I'm getting the value correctly, so that's good. Now what I'm going to do is to apply this contrast value to a density attribute so that I could use that density to scatter the point based on those values. So when you do the scatter points on the mesh, which has the density attributes, you could check this density attributes on, then should be able to, the point's position will use the density attributes to scatter the point based on these contrast value, the density value. Now you could increase the point number to something like 5,000, should be enough. Okay, so let's go with this. So let's say this is the initial state, initial point position we want to use in order to create a optimal path using a TSP, Travel Salesman problem. So what I could try first is to add a polyline which connects all the points together. So maybe you can use add node to connect all the points together like this. And maybe this could be initial state to solve the problem. Although this is too complex, you have tons of like intersections, crossings, so I can easily see that this is gonna take a lot of time to solve. So next thing you want to do is to make sure that the initial state is clean as much as possible. Even if you have crossings, try to make the crossing less as much as possible. If you try to do the optimization with this, I'll show you, but it's gonna take tons of time to solve it. Now in order to solve it, I would rather use solver instead of using for each feedback, because you don't know how much iterations you're gonna need in order to solve the problem. So it might be better using the solver in this case. So you just need to copy the 2opt code, 2opt attribute wrangle that I've created here inside the solver, and also connect the second input over here. Oops. Second input was used to estimate if the curve is closed or not. Okay, now this one, let's say if this is closed. So in this case, you're going to connect it to the first input, then convert it into a line and connect that one to the first input. Now this should be all okay in order to start the optimization. Now let's see what would happen with this setup. I'm guessing it's gonna be really slow to solve. So if I start it, you can see that it does seem to change something, but I don't really see what's happening here because there are so many connections, so many crossings here. It might take like tons of time to solve it. Okay, something is happening, but not sure what that is. Let's try to reduce the number of points to like 100 maybe. So let's see what would happen with these. If it's 100, maybe it's a bit faster. So you could see it is kind of solving the problem. Try not to cross the curve over time. But as you can see, even if with the 100 points, which is small number of points, it takes like 400 frames to solve the problem. Okay, which is a lot, I think. So the next step is to make sure, even if you have a high number of points, in order to solve this as quickly as possible, try to optimize the initial state without using any optimizing or without using TSP. So to do that, let's go back to 5,000 points, and one thing I could think of is to sort the point in order. For example, sort the point in X directions. That might give you a bit cleaner order, the cleaner order for initial status, how the point is being connected as a polyline, or using spatial locality might give you a better result like that. Okay, this already looks better, much better than the random point connections. So let's see how it goes with this spatial locality order and see if it's gonna solve the problem quicker or not. So if I run this, I can see that it is running a bit quicker, although it does trying to solve one by one, so it still asks you to wait for a lot of time to solve the whole problem. So next thing you might want to think of is how you could do this multi-threaded. Like maybe you might want to solve this part, these part, area by area. You might want to solve it at once, not just solving one by one like this. So let's think how we could do that. Now one thing you could do as a brute force way is to increase the sub steps, but this will give you a high calculation cost, which is not really optimal. So this is kind of what I want to avoid doing it. I want to keep the sub steps to 1, but to make as much fast as possible. So to do that, what I can think of is, well, there are several things that I could think of. One is, since what I want is a picture. What I want is the result which does not have any crossing, right? Which so maybe I could only pick those edges which only have the crossing area, okay, and solve those edges which has the crossing problem once. Another things that I could try is make the region divided into some steps, or maybe in grid, maybe divide these image into like 5 by 5 cell by cell and let's say you could just solve the TSP problem at this part, at this part, at this part, and so on, and then increase the size of the area you want to calculate over time. So as initial state, you could try to solve the problem from small size of the grid. Then in the end you can maybe try to solve it with the whole picture. That could also be one things you could try. Now, first thing I want to try is to pick the curve where it has a intersections and just solve those intersected curve. So shall we do that? Shall we try that? Now to do that, the idea that I have is to first of all check which part is being intersected or which part is being crossed. Like for example, it is pretty obvious that this long curve has a bunch of crossings, and this one's also having crossings and so on. So what I want to do is to solve all these crossings one by one, and probably preferably in multi-threaded way. So to do that, first thing first, you need to make sure you find the crossing part. So let's see, what you could do is to first of all use a node like an intersection analysis, which will give you a bunch of intersected points between the curves, which also gives you intersection between the self-intersected curve. Now sometimes it also gives you just the corner points like these, which is not optimal, so let's make sure the proximity tolerance is small enough, which will only give you an actual intersected points like these. Okay, so this is not intersected, so this doesn't give you any points. That's good. Okay. Now next, let's look at the information that I got from this intersection analysis. Let's go to a point geometry spreadsheet. Doesn't give you any informations, but once you check these infos like input number, primitive UV, and so on, give you all the informations you might want, and the one that I want to know is this source primitive information, which gives you which edge and which edge is intersecting. So for example, for the intersection 1, this says number 3 and number 1 is intersecting as an edge. So what I could understand from this information is that I need to optimize the curve which is at this range here. So from 1 to 3, this is where it's creating a intersections, which is somewhere around here, right? So it says 1 and 3, did it 1 and 3, and it says this, so this is 1, is it? Not sure if this is actually giving the right value. Okay, so this is 1 and this is 3. Yeah, so it does seem to give you the right intersection. So the first intersection points is right here, and you have intersections right here. And what I can see from this is that in order to optimize this, you just need to like swap this edge right here. And in order to optimize this, you don't really need a whole curve, like the whole curve, but to just locally optimize it, you just need the curves around these curves. So maybe just pick those curve which is in between, I don't know, 0 to 4 might be enough to solve just this part, just this intersected parts. So because I'm just picking up the local curve connections, it should not take much time to solve this small amount of edges. And if I do this kind of a local optimizations for each of the intersections, it will take less time to solve like multi-local positions in one time, I think. So it's kind of a reason why I'm just getting the intersected points to just see in which parts I just need to optimize. So let's see if this is gonna work. So in order to retrieve the primitive number which can be retrieved from the intersected point informations, and also get the in-between edge like these one, and maybe some curve offsetted from the first and end points, 2 or 3. What you need to do is to access to each of the point attribute, which is this source prim. So let's try doing that. Okay, so first thing first, let's get these two informations. Sometimes it has 3. Let's check. So most of the time, since 2 curves are intersecting, you only have 2 intersections, but sometimes you have 3 in some situations. Well, in those cases, I'm just going to get the smallest and the largest and take the number in between these two. And sometimes it also goes from really big number to the small number. Like currently, do I have, yeah, something like this. So this shows that this is not actually from 8 to 4,999, but the one you might want to look is in between, goes incremented from 4,999, and after going above 5,000 it goes back to 0. So sometimes you might want to go upward, sometimes you want to go downward in terms of the counting. That's what you want to be careful of, because if you try to optimize in between 8 to 9, 4,999, that will be too much number of curve to optimize to look for. Okay, so what I want to make sure is that the difference between two point numbers is less than the half number of the total points. The total point in this case is 5,000 points, so if the difference between two is more than 2,500, then you might want to go to the other directions to connect between the points. Okay, so in this case, you might want to go from 4,999 to 8, not from the other way around, other order. Okay, so that's one thing you need to be careful of. And let's see. So I'm going to use the point wrangle to get those information first. Okay, so int pt1 is source prim 0. pt2 is, or we actually don't really know what's the minimum, what's the maximum, so maybe I could name it like this. So the minimum point is, I don't know, well, this might not be the right value. It's really hard to say. Well, let's just start by a really big number, and the maximum point number is to really small number. Then create a loop for all the source prim numbers. Check the current source prim. And if the source prim is larger than max pt, update the max pt by source prim. If the source prim is less than min pt, update the min pt by the source prim. Okay, let's check what we have here. Okay, so we have min pt, max pt. Yeah. Now, that's good. Now, one thing that I need to be careful of is to sort these point. Let me check. Let's see. Now I also want to make sure that you don't have the same number for max point and min point. If you have the same point, then that means it's not really intersection part, it's just the same point. So in those cases you can just delete that point. So if min pt is equal to max pt, then just delete that. Okay, did I change the number of points? No. So there are no duplicate points. Okay, that's good. Now other information that I could create is so these informations, right? So we have, especially for these ones, I want to make sure that this one this number will be the starting point and this will be the end point, because the difference between these two is this is difference between these two is bigger when you make this number starting point and this number end point. But if you make this point a starting point, then the difference will be somewhere like 10. But if it's the other way around, then the difference will be 4,991 or 90. So that's not good. So one thing that I want to make sure is subtract the max PT minus min PT, calculate the absolute value and check if it's more than or less than the half of the total point number, which I can get it from here. Okay, so if this is true, then you might want to make the max PT to be the starting point, start PT, and end PT to be minimum. Else make the start PT to be the minimum and PT to be the maximum. Okay, so let's check. So in this case, it's not doing what I'm hoping it like. Okay, it was the other way around. It's minimum PT minus max PT, I think. Is it? Maybe not. Oh wait, this is not. This is correct, but this should go all the way around. So this should go to here. This should go to here. Okay, yeah, should do it. Yeah, so if it's smaller than half of the size of the point number, then it's okay to start with from minimum point number to the max point number. If it's not, then start from max to min. Okay, that will do it. That should do it. Alright. Now, I also want to calculate, I also want to have this information, the difference between the start point to the end point as a value to graph the length of the curve that you're trying to optimize. So we could start from the smaller length of the curve to start optimizing, then go to the longer one in the last, probably. Or maybe other way around, I'm not sure which one's better. Let's try to get that information. So, to get that kind of information, what I could do is create a information called sort, starting with 0, and here the sort could be a end PT minus and a start PT. Simple as that. But for this one, it's a bit different because you have a value like this. So in this case, what you could do is you just want to have the difference, but so So let me see. Let's see. So in order to get the right sort value, this could be done by the number of points subtracted by the start PT plus end PT. Let's see. And try to give the sort to an attribute and see what kind of value that I get. So what's I think I'm misspelled somewhere. Why am I getting star PT? Where is it? Star PT. Okay, start PT. Okay, so the sort is within 1,000, so it should be correct, I guess. This is pretty big, but comparing this one and this one, this seems correct. So this is a starting point, this is a end point, and this is the differences. Okay, so that should not go over 2,500 and everything looks good. Okay. So George, hello George, what programming language is this? It's Vex. Yeah, it's Vex, Houdini scripting language. As Alexander said, it's mentioning it's based on C. Yes. Okay, so where was I? So sort. Got the sort info. Now I can use a sort node to kind of actually sort the point based on this attribute that I've created. Sort. So that minimum value comes first and the larger one comes later. This means that this has small lengths of polyline in order to solve the crossings. Okay, so we can start by solving these smaller polyline, then go to the other curves later. Let's see if that is gonna work. So after having these curved sorted out, what I'm gonna do now is to use a for loop and decide the number of polyline you wanna solve in multi-threaded. Let's say 100. I'm not sure 100 might be too big, but let's see if it's gonna work. And want to make sure that this is a feedback loop, so make sure that it's got feedback H iterations and fetch feedback. So since it's going to be a feedback loop, I'm not really sure this is going to be counted as a multi-threaded one, but I'm also going to apply this multi-thread when compiled. So I'm also going to implement a compile block to hopefully make this loop a multi-threaded loop. Okay, and the curve that I want to optimize is not the intersecting point but the actual curve. So let's connect the null node here, call this curve, and connect it to the for loop here. Okay, now what I want to do is to bring these information right here, retrieved right here, inside the loop. So let's connect this, and let's name this enter. Okay. Now, in order to be able to use this inside a compiled block, I think you need to have an additional block begin node created and connected right here. Okay, so that you can use it inside the loop. Alright, so next what I'm going to do is to copy the one that I have been creating to do the optimization using 2-opt algorithm inside here. Okay, now I also want to connect several informations to this attribute wrangle. One is the curve itself, which gives you the total point number. Right, so in this case I might need another block to connect. Well, maybe I can just get the point number from this first input, maybe. No, I mean I needed the closed info. I needed to know if the curve is closed or not, so not from here, but should be retrieved from this node. This is showing if the curve is closed or not. Okay, that's good. Now going inside the code, you also want to connect this intersection information to see which part you want to optimize. Okay, and currently you have like 2,419 points, intersected points, which is a bit too much to solve. So what I would suggest is to reduce the number of intersections into the same number with the for loop count iterations. So currently I have 5 iterations, so let's copy that number and reduce the number of intersections to that number. Since this is already being sorted, you're getting value in between 0 to 99, and which has the shorter lengths in terms of the polyline, which shares the intersected points. Okay, so now we have those points, and going inside the attribute wrangle, what you want to do next is to get the intersected point informations. And in order to do that, you also need to know in which iterations you're in right now in terms of the loop. So let's also connect this for each count to the 4th input, and let's get that information first. The current iterations of the loop is like this, and from this informations you can get the corresponding intersected point information, so which in this case the same number as ite. And from the intersected point information, the information you want to get is the starting point number and the end point number. So start pt and end pt is the value you want to get. Yep. let's check. Yeah, so let's get that information. So start pt is, actually this is not a pt, but it's actually a primitive, wasn't it? Yeah, it is a primitive number, I realize. So let's go back to where I was sorting the informations. I was writing like pt, but actually it was primitive, so my bad. I think I need to rewrite this. Okay, so how should we do that? Well, I'm gonna name this min prim, min max prim, min prim, and max prim. And what I actually want to do is to also retrieve the point number from these primitives later. That's what I will need to remember. Okay. Just a name convention, but it gives you confusion if I write it like PT, so it's better I rename it. And these are not a PT but prim. These small details kind of really matters. Okay, prim. Okay, so did I get everything right? Nope. Prim. Okay, check. Alright, so we have end prim and start prim. Okay. So this is a primitive number that I was getting, and coming from the third input, start prim at iteration. Point second input and prim iterations. Alright. So what I want to do next is to update this start and end point number from these primitive numbers. Okay, and these primitive numbers are related to the one that's coming from the first input, which is these edge numbers. Okay, so what I need to do is to retrieve the starting point and end point from the primitive and replace that with start and end. Okay, so that's what you need to do, right? But actually you could just get those informations right here. That might be easier rather than retrieving all those information again and again in the loop. Let's just give those starting point number and end point number right here. That might be better. Okay, so since we have these curve information connected to the second input of the sort info, I could actually get the starting point and end point from these. Okay, so let's do that. So after I got the primitive number somewhere around here, let's get a start PTS by using prim points from the first input, I mean the second input, using the start primitive number, and also prim points. Okay, now the start PT in this case will be the first point from the start PTS. It's pretty obvious. And end PT will be the second point from the endpoints, which is the endpoint of the edge. So that's that. And you do the similar thing right here, but the order is different, so you need to be careful which point is you're getting. So the start point will be, in this case, 1 and 0. Yeah, because it's the other way around. And that should be it, I think. Where is it? Let me think. Start primitive. Actually, this is still 0 and 1, I guess. Isn't it? Yeah. Yeah, I think so. Now let's try with these. I think this is correct. So if that's so, maybe I can just do it outside the conditions like this. Isn't it? Yeah, I like that. think this works like this. Let's see. So we now have a starting point and an end point, which can be directly used as a start and end, I think. So let's try that out. So instead of you getting the start prim, you could just get the PT and PT and PT. Okay, then update this value to start PT and end to end PT. In this case, +1, I believe, because endpoints is not the endpoints, but the number of points +1. I mean, the end point number +1 is the endpoint, so this should be like this, I think. Let's see. So after that, it should all be okay, hopefully. Let's see if it's gonna solve the issue. So if I, oops, getting an error. Strict nesting, incompatible compile block begin, encountered while block end. Okay. Maybe I needed to create a additional begin block here for the loop, using it to fetch input, connect like this, and do the same with these. Yeah. Now let's see if it's gonna solve it. So we'll reconnect the out to the end of the compile node. See what would happen. Okay, well, it does seem to solve, but it's pretty slow, is it? Does seem to solve, but it's pretty slow. I can say that it's pretty slow. Let's see if I need to reduce the number of iterations. Let's say if I reduce the number of intersections to 10. Let's also check if which part is getting the higher calculation. I mean, which part is getting the most high processing cost. So if I play it, so obviously inside the compile node, which is a bit hard to see, so let's remove the compile block temporarily, see which part is giving you the high computation. Now obviously this one, yeah, of course. So maybe it's not being really optimized yet. Let's see why. So first thing I want to make sure is that if I'm getting the right value in order to do the calculations. Let's try to reduce the feedback number to 10 to see if it's gonna solve anything. So if I play it, yeah, it does seem to run, but it's not that fast. It's getting slower and slower. And I'm guessing is because the length of the polyline is getting higher and higher. Although it's pretty small. It's pretty small. That does not make sense. Huh. We only have like lengths of 2, so it's pretty small in terms of the length, so it shouldn't take that much time to solve this. So maybe something is wrong inside the loop. So we have, wait a minute, do we have a start point? Start PT, do we have it? Okay, yeah, we do. So start PT and NPT, I do have it. Let's see if I'm getting that value correctly. I want to check in this code. Check the value within the attribute. Ah, okay, so something is wrong. Start is not correct. Oh wow, this is wrong. What I needed to do is to subtract by 1, not just updating it to -1. So that was the problem. Okay, so I guess that was it. Let's go back and see. Let's increase the iterations to 100 again. Should be okay. going back into the geometry node and okay, so it's much faster. Now getting slower because you have this really long curve weighted, which has tons of intersections I can see. And it did go well till some part, but it's getting slower at this point. So let's see what's wrong. What can I do to solve after this? So let's check the intersection. So we have tons of intersections with these long curve, and I assume we have a really long like edge lengths which covers this intersection, so which is from from start point to the end point. Now funny thing is end point is everything is the last point number. Is that correct? Oh yeah, well this is not the point number, but this is the primitive number, so the long, I am guessing the long curve is this number. Okay, so I can see that wait, you can see that the longest one is something like this one, which might be the reason why it takes so much time to solve, because this is really long. Let's check. So so this doesn't really look correct, is it? Again, stop at 0. 1, 2, 3, 4, 5, 6, 7. At some point it becomes 1 and -1, and I guess that is because it goes over the number of intersections. So I also need to make sure that this number should be less than the number of intersections right here, getting right here. So n primitive enter and minimum 100. I think I'm getting some errors here. Why am I getting errors? Okay, so it's also using a value right here. That was the problem. Okay, so I'll just hard code the number like this. Then doing it like this. In the end, wait, the number do I, oh, okay, this number of points, so should be n points. Okay, wait a minute, why it's not? Let me go from the start then. I can reset the current situations. Let's see, play. Okay, so getting slower here. Let's see what's happening. So I'm still so this is correct. This should be the number of the maximum number of points available from the intersections. Yeah. Now the value that I get here is from start to end is pretty big, so I guess that's the reason why it's taking a lot of time to calculate. So I could see that it will take a lot of time to solve this. Even with the multi-thread when compiled is on. So as a solutions, one thing I could think of is to kind of optimize the initial state. Try not to create this long crossing line as much as possible in initial state. That's one thing you could try in order to make sure that you are not getting these long crossing curve. One thing I'm kind of worried is that it might not be picking up these line to optimize. Wait, what's happening? My mouse has been stuck. Oops, what's happening? Let me reopen the file. Okay, something is wrong with my mouse. Kind of stuck. Let me reopen the Houdini. Does not seem to work. Let's save this. Try to reopen it. I think something was off with the previous one because the longer one should be getting smaller, but it wasn't. So maybe something was wrong with my implementation. So let me check. Okay. Let's go till somewhere around here. It's kind of weird that it's only like solving this small part and not solving these long part, because you should be able to have a smaller length by solving this long length curve. So that's kind of weird. What if I change this back to 0 and this one to endpoints 0? Would that solve it? Yeah. So maybe something is wrong. Or maybe let me try with this setup. Yeah, this is kind of slower because it's try to just look for every connections. Okay, well, so this was okay till some point, but at some point this is not working well, especially when the curve is, wait a minute, something has changed, not sure. So I have set it to start point, yeah, then we have end point. What did it change? I'm getting some different results from the previous one. Not sure why. Why is that? Do I still have intersections? Yes. Oh yeah, well, still getting it. So okay, so let's see if there's anything that I could do at this point. If not, then I will try to optimize the initial state, try to optimize the sort for the initial state, but there is one thing I kind of worry about at this point. Maybe optimizing this part is not currently working correctly, so let's check that. Let me go with the single pass somewhere on here. Check the maybe not the single pass. Just want to get the end result. Was the same. Now let's try to color these points and see if this long curve is included in the list or not. If not, then there's something I'm doing wrong. So this is the point number. Okay. So I plus 1 j plus 1. Okay, so seems like the curve, the starting point or end point of this curve is not included with these points, so that was the problem. So for that purpose, what I could try is I could just go like negative, I don't know, 5 or 3 or 2 and plus 2 to increase the range, and now it is included. Maybe that was let's give some margins here. Okay, since this is not like calculating every point, it doesn't really matter if it's closed or not, I guess. Anyway, this should be good. guess this should include all the points that I need in order to optimize. What if I increase this one? Doesn't change. What if I decrease this one? Doesn't really change. Okay, so let's go with these and see if I get a better result with these. Alright, so disable the coloring, going back to the geometry node and see if we could solve. Okay, so that was faster. Now it did kind of solve the intersections, but now we do still need to solve the shortest path problem, because as you can see, this is not really clean at all. So right after you did the intersection problem solving, the next thing you want to do is to kind of optimize the path using the original like opt2 problem to kind of solve the shortest path problem. So solving the intersection doesn't really gives you the shortest path. You do need to look the whole curve in order to finalize the optimization. Meaning you do need this process right here. So let's do that. So I think it's a good idea that when you are having no intersections at all, then you could switch back to the original 2-opt algorithm for the whole curve. So give a switch, connect it here, and count the point number on from the intersect null node. If it's 0, then use this one instead. So endpoints enter 0, then use this opt point. Let's see what happens. Now the intersection solving has been done. Then it start optimizing using the whole curve, but it still is slow because it's just optimizing the small location parts by parts. So maybe this part could also be using some kind of optimization method to kind of a multi-thread, kind of solve it in multi-thread. Okay, so meaning just looking at the whole curve at once is again a bit too slow. So in this case, maybe we can split the whole curve into a grid and just pick those grid part to solve only those part. And maybe in the end you could increase the number of size of the grid cell to include the whole curve. Okay. So let me check the comment if you guys have any questions. Can we use Python and Houdini? Yeah, you could. Hello. My first. Thank you for all the comments. Hopefully I get something out of what I'm doing. Now let's try optimizing it. So to do that, I'm going to split each point into a grid number. So to do that, I am going to create a point wrangle, maybe beforehand, before the solver, somewhere around here. Okay. And what I would like to do is to think of some grid covering the image, which could be things like this, and kind of subdivide the primitive into a bunch of cells like these, and copy maybe the primitive number of each grid to a point, and only calculate the curve which is included inside this grid number one by one. So meaning I would like to calculate only the points in each cells at once, and maybe in the end I could increase the size of the cells like this, and finally this. So maybe using subdivisions might make sense for that purpose. So shall we try that? I mean, I haven't tried this approach yet, but hopefully this works. I'm going to create a for loop to define how many subdivisions that I would like to create, maybe 3, and each time I'm going to create a subdivisions, and right here for the depths I'm going to use the iteration number for each count 2. This always starts with 0, so I'm gonna add it by 1. So as a result, if it's just 1, you get just 1 result. Maybe actually I could start from 0 so that I could have the whole shape in the end. Alright, and let's start like these. Okay, so for each primitive, going to give some attributes information, since we are merging all the results. Each cell should have a information like iterations first of all. So 0 is the largest. But I kind of want to go the other way around, so I'm gonna go like this. First of all, get the number of iterations and subtract it by the iteration -1. This will give you why it's a negative. Iterations. Okay. Okay, so starting with 0, then the biggest square will get 3. Yeah. So 0 is the most splitted grid. The 3 is the just 1 square. 2 is 4 squares, and so on. Okay. And what else do I need? Okay, I also need the primitive number information, so I'll just copy the primitive number as it is. This will be used as an ID. Right. Okay, so that should be good. Now that I have this information, should be connected to here. Next, I could use this to copy the informations to each point. Okay, so I'm gonna connect this to here. Um, let's also copy this iteration number value as a parameter here. Okay, and this is actually a number point, yeah. Okay, so I'm gonna make a loop with this number of iterations, and for each iterations I want to I want to sample the value, which in this case I want to sample this primitive number correspond with the iteration number. So let's do that. In order to sample the value, I guess I could use UV sample. Guess this is the easiest way to do. From the second input, from what was the second parameter for UV sample? Attribute name, string attribute name, prim group. So we do need a prim group, I think. The prim group is iterations is equal to I. Then the information that I need is prim num, but I realized that this, when using UV sample, this has to be vector value, I think. Let me see. No, I don't remember correctly. Let's see if I can get it. Then using P as a sampling value. Okay, let's see if I be able to get this value correctly. And as a parameter, how do I apply it? Should I apply it as string? So it's I2A I plus prim n. I2A. So do I get those informations? Nope. Everything is 0 here, meaning I'm not getting a right value with this. So that's not good. And I realized that is because this is not a point attribute, but this is a primitive attribute. Maybe that's why. Okay. In those cases, instead of using UV sample, I am going to use XYZ distance. This part is the same, but instead of using UV sample, I'm going to use XYZ distance, which will give you a primitive number, and from this primitive number you'll be able to get a primitive number and prim n. And hopefully this will give you an information. Not, still not. Maybe I'm doing something wrong here. So looking at the primitive number, I do have iterations, prim m, prim n. Yeah, that's good. Now for each iterations, oh wait, I shouldn't shouldn't override the informations like this, but I think I should have it as an array. Okay. So, how's this? Everything is 0. Nope. Actually, I am getting some value here. So that's good. That's good. Yeah, I think it's correct. I think this is correct. So the last one is everything is 0 because this is just one rectangle. Makes sense. Okay. So this is the information that I need, and I am going to use these information to group the points together to see which parts should be calculated all together. Okay, let's go back to the solver. And I also need to make sure that these informations is being transferred correctly to here. Do I get it? Am I getting that information? Nope, it's not. It just disappeared. When did it disappear? I have it till here. Why I'm not? Okay, maybe I needed to reset the simulations. Okay. Alright, so going back to this place. Now let's give another for loop, shall we? For a multi-threading. Okay, and it'll be a bit complex because you have like subdivided paths, subdivided group, and you might want to change it over time. Let's use the compile block again. So that I can turn on the multi-thread when compiled. And let's also make it a feedback loop. I'm not really sure if the feedback loop also works with the multi-threaded. Usually not, but let's see. Okay, so going back to the input. So I have these points and I want to group those points based on those values inside this prim ends. If you're sharing the same number, you should use those points all together to calculate the OP2 problem. OP2 problem. So let's see. I'm just going to copy this one and let's connect the iteration here. The starting point could be defined inside here, and the loop can be stated by just picking up the first number of these prim m's So the number of loops should be equal to a number of different values inside this premen's. Okay, which should be easy to get. Let's go back outside of loop and let's get the maximum number of premen's as an information, so that you just don't need to recalculate every time. So you could do that by set detail attrib. Maybe not. I'm just gonna add it as a primitive attribute. I'm gonna say number of primitives. And this will just do it. Okay, so we have number of primitives. This is the maximum number of primitives. And I could just copy that information to each of the point. Okay. Let's get the number of primitives. Like that. And then okay, am I getting it? I'm getting an error here. Missing a parenthesis. Okay. Okay, is this correct? So number of primitives. Why is it? Should be 1 for the last one, so I think it's not correct. I don't think this is correct. Although these values seems correct, so maybe the sampling part is wrong. Numprims. Oh, I forgot to do this here. Okay. Now, okay, everything looks correct. So yeah. 64, 16, 4, and 1. That's good. Going back inside the solver, then try to get that information right here. From each point has that information. So let's get that. S is equal to okay, well, we'll reset the simulations, and I am still not seeing. Okay, numprims. Huh. Why is it not okay? And we have numprims. Now, just to make it easier, let's just try with the first value inside this array. So numprims. Okay. So let's just get the first value from each one of them. Okay, now these value indicates especially the number of prim indicates the number of loops that I want to run. So actually I should get this value outside the loop, probably somewhere around here, so that I can use it for this iteration. Okay, so I'm gonna give additional attribute wrangle as a detail, get the number of prims from one of the point, which is all the same for every point, so I can just get from any points. Then get the first one, set it as a temporal attribute value, like that. Then connect the null node so that it's easier to reference. It's not really a subd, but let's just name it like this and refer to that null node by accessing to a detail attribute called numprim, which I don't have it right now. Why? Why am I not getting the value here? Why don't get... Okay, so first of all, numprims from point, is this correct? No. Yeah, it is correct. Numprims, getting the point attribute, right? Why am I... Funny. I am not getting anything here. Why is that? Why is that? Huh. Not sure why. Reset the loop. Huh. Let me recreate the attribute wrangle and see. Wait a minute. I shouldn't connect it with the input 2, but I should connect it to the preframe. Why did I connect it here? I guess that's the reason why, isn't it? Nope, still not. Still not correct. So I'm using a detail wrangle, updating the value with some values, and I should be able to see. Okay, I do see here. So why I'm not seeing here? It's weird. Let's reconnect it here. Huh? Disappeared. Am I not allowed to use this? That's the reason? Okay, maybe it's the name was taken by some other attribute. Maybe that's why. Okay, didn't know that. Didn't know that. it should give me some errors. Okay, so this should be okay. So I have 64. So let's get that value from new node, detail subd n prim 0. So I got 64. So doing a 64 times loop, 64 iterations of loop, then for each loop you get this iterations number, and now the next thing you will need to do is to kind of come up with the starting point of this part and end point of this part. Now there is a chance that the point that being retrieved from the grid positions is not really connected to each other, so you gotta make sure everything is being connected by getting the retrieving the minimum and maximum number from the point you get from this list, then use that to connect the whole overall places, connect the places which might not be included in the grid. So first thing first, I'm gonna give another point wrangle just to trim the point which has this number, this value called a prim MNS, this one. So if prim NS, was it prim NS 0 is equal to iteration or not equal to iterations, could remove those points. Okay, and you are left out with some part, and there is a chance that this is not connected as one line. Well, luckily this is connected, but maybe I need some samples which is not connected. So let's see, let's look for some part where it is not connected. Or is it forcibly connected? I don't think so. Kind of a weird that everything is being connected as one line. Is this supposed to happen like that? I'm not sure, but it does seem to. Well, I was hoping some split between the points, but from what I see, I don't see any split. So maybe let's, just for testing, I'm going to raise the the subdivisions just one above. So number of prims, and change this to 1. Now this should give you something like this, which I think in some part it's been disconnected. Is it? Hopefully. Otherwise it's a bit hard to test. Maybe not. Maybe the way I sort it using a spatial locality sort is actually using the subdivision sort. So maybe it's pretty optimal for subdivisions. Huh. That I didn't know. If that's so, then that's more easier for us to, because we don't really have to think about the disconnections. That's good, I guess. Oh, although I realized that there's a chance that there's gonna be a disconnection after being optimized using this intersect optimizations thing, right? So right after, somewhere around here, you should be able to see some disconnection. Okay, so, but now that well, anyway, let me see. So yeah, I think I am already seeing some disconnections, as you can see here. So let's go back to the first value. Yeah, I do see some disconnections, and oh, well, it's not really on the grid. That is because I am changing the point position over this first optimization using intersection. So actually the order itself for the curve is not really changing. So after all, maybe I don't really need to care about the splits. Okay, I mean, that's good. That's good for us, because it's kind of easier for us to deal with. Alright, in that case, it's kind of easy to estimate the starting point and end point for that. So let's see. I could still use this thing, and before removing every point, I could copy the current point number. Wait a minute, no. Yeah, I could copy the current point number to something like PTN. PTNum. Okay, which will give you all those informations, PTN. Then just get the smallest one will be the starting point, and the largest one will be the end point. I think that'll do the job. Or just get the starting point from this polyline and end point from the this polyend, and use that as a start and end point right here. Yeah, should do the job. So connect it to the second input here, and do I need if the curve is closed or not? Nope, I don't need that informations, so I don't really need this. And actually I don't really need that information here as well. So let's just remove that. And then the starting point. Well, from the second input I could give a bunch of polyline points from the second input by using prim points, which should wait a minute, not really. I could maybe I can just get the first and the last point from the second input. So PT1, the start point is point second input, and get the point number, the first one, and end PT is point PTN, which will be the end point number, so from the second input. Okay, let's check PTN. Let's see if I'm getting the right start and end value here. Am I running on the detail? So start and end looks correct, yes. And all the other rest of the stuff should be the same, and let's see what happens. Is it optimized? Not sure. Let's go. Let's go and see. And at some point the optimization ended with the subdivided part. There's nothing more to optimize, so in those cases you might want to increase the number of iterations for the subdivisions. Let's see. Well, problem is it's still at 0, so there is still intersections. Huh. There's still intersections. Is it? Yeah, it is. There are. And it's not really solving the problem. Maybe that's a little bit of problem. Okay, I need to go back here to see why it's not solving here. Okay, let me recolor this. And I see that it's not being colored, meaning it's kind of ignoring these intersected place. Well, that's not good. It's not really good. Gotta make sure that if I'm doing this correctly. What if I make this -5 and 5? Nope. So let's check the start and the end point first of all. So the start is 4702 and the end is 92. Okay. And and why it is not working. So it's going from start to end. Okay. Now realize if I start from here, then do the loop end at 92, this loop is not going to run at all. So that's a problem. Wow. Fix that. Let's fix that. Okay. So to fix this, let's go back here. And where I was setting the starting point and end point, maybe I should really fix for, maybe I should really fix it. Right here inside. So this one is okay, but this part, if the starting point is larger than end point, then in this case the trick that I could use is to increase the endpoint by the total number of points, and that as a result will give you a number which is larger than the total number of points, but then inside the loop will be calculated with the modulus, so going back to 92 again. So it should be okay. And then yeah, we do have this color. Now hopefully this will solve the problem. Let's go back. Okay, now seems like intersection is all solved, hopefully, and switch back to a second loop, which is this one, and this is also being calculated. Gotta make sure I have some check system to see if the optimization in this subdivision part is being ended or not. So in order to do that, one way is to calculate the lengths for the whole curve, if it's being optimized or not from the previous state. So to do that, I could use a measure node beforehand, calculate the measures beforehand, perimeter throughout, get the total parameter as a 1. Let's check the lengths. So it's this one before the optimizations, and it's also check after the optimizations. If it's the same, then nothing has been optimized. So in this case, what you could do is to increase this number by 1 until you get the whole square as a subdivided shape. Alright, so let's count, let's create some system to check these two parameters. I'm gonna use attribute wrangle for detail. Get these two values. Total perimeter 1. Okay, and if the difference between these two values is small enough, then increase a value, a subdivision value. So let's give a value name, attribute name called subd, and increase by 1. And initially, when you are choosing iterations here, you also want to use subd here. And I don't really have that initial attributes in it, so let's also create that before get it inside the solver, somewhere around here. For detail, subd integer starting with 0. Okay. Now and you also want to make sure that this doesn't go over the maximum number, which is the number of array retrieved from the point. In this case, the maximum number of subdivisions is 4, so it shouldn't go over the number of arrays. So if it goes over, then the final switch you want to do is to skip whole calculations. Okay, so let's have the number of arrays as a detail attribute somewhere, maybe outside the loop. As a detail, number of subds is by getting, first of all, getting some arrays, num_prims from point, one of the point. And then the number of subds is this number of arrays. Could be any point. So this 4. Okay, now as in order to apply a conditions, maybe I could read a value right here on the curve. If the detail curve subd is larger or equal to a number of subdivisions, which I don't see it yet. Reset the simulations. Where is it? Should be getting as a detail nums of these. Yep. And I should be able to get that information here. Yep, nums of these. So if it's more, if the subds is more than num subds, then you should just do nothing. Just activate the null, or just give the curve as it is. doing nothing. So hopefully this will do the job. And okay, going back to where we have here, we also need to use subd right here. Okay, which is on the detail, so let's get that. How's this? So starting from the small grid cells, and if you don't find any optimization for that cells, then it increase the size of the cell to make more larger optimizations going forward until going to the last big square. Hopefully this works. I'm not sure. Let's see. Start. And I do see some small optimization happening, but does not seem correct, is it? The curve isn't really look like it's been optimized, is it? Let's see. What's the current subdivisions? It's at the end, so it's supposed to be ended, but let's see if I connect this one here. This is the original one, which just solve the whole curve. And if it's still solving, then something is wrong. Yeah, it's still solving, so something must be wrong. So I think I'm missing something here. When this part runs, it should not do any optimization. Okay, so what is wrong here? Let's see. First of all, let's color this. It's a pretty small part. It's not really correct. It doesn't seem correct. Let's go back to somewhere around here. Okay, so till here there was some optimization happening. Now this was when the subd value was 1. Okay. Right. Getting bigger. Oh, this part. Forgot to check off this single pass. That's why. Stupid me. Of course it's not gonna work. Alright. Am I doing correct for this one? Yep. Okay. Let's go back again and check. Okay. Looks much better than the previous getting better. Yeah. Yeah, I think it's getting better. I mean, the curve seems optimized. I guess it's in the last part for the optimization. Alright, then when you have this fast tracking happens, it means there are no more optimization to be done. So I believe this is working. Yay. Now let's try with a little bit more points, like 15,000. Is it still gonna work or not? Let's also increase the number of subds to 5. Okay, let's try. Still looks pretty fast. Overall, not really bad. It does take some time for the final optimizations, but still much faster than the just making the initial pass so random. So you just gotta wait a little bit in order to solve this problem for the final step. I mean, if you want to make it more faster, then you could try dividing with using different method other than like using subdivisions and stuff. But as I said, the important thing is to make sure that the initial state is clean as much as possible. I mean, in this case I have used spatial locality to sort, but previously the one that I tested initially was with a different method. With the one that I have tried previously, I have sorted in my own using my own sort functions, which is a bit more tedious. But what I did is to create a network sort by dividing the grid of your own choice, then, which is this one, then create a like a sorted grid going from right to left to right to left, and just connect back to the first point like this. which seems to gives you a faster results than the spatial locality sort, because you could give any number of divisions as you want like this. So more divisions you have, get faster. Let me just try running this to see the difference. So compared to the one that I show you, it runs like a scan line and solve it pretty quickly. That is because the initial state was a bit more cleaner than the spatial locality, I guess. That's the reason. So I'm gonna upload both files, the initial files that I created here as well as the one that I tried on live. The one that I tried on live is a bit dirty. I mean, look at these curves, it's not really, doesn't really look pretty. So you can see that just by changing the initial state, it just changes the way it connects pretty drastically. But still, no intersections. even for this one. So yeah, seems to work. You have, yeah, but as you can see, if you have more numbers of points to deal with, gets more, and you do need a lot of times to solve this. Okay, well, that's pretty much it now. Hope you liked it. I mean, yeah, I could, yeah, well, let me see if I could. There could be a chance that there might be a chance that I might want to also decrement the subds at some point to check if it could redo the subdivision part from scratch, especially after I have solved the intersection. So let me add additional stuff in for just the testing. Not sure if it's gonna work. You always need to test. Make this back to 0 after the intersection fixing. That might make the whole step a bit faster. Yeah, I do see some improvements in terms of the speed, I guess. So as soon as you find an intersection problem, it will start off from the small grid cells optimizations. And continue doing it. Now, what's the smallest grid size? Okay. Just seems like it's keep fixing it. Well, just gotta wait for the final result. Although I don't really like these parts. It is not intersecting, so this might be kind of okay, but this is due to the original, I mean the initial sorting, which is using a spatial locality. So this is pretty up to this part in order to make it faster. So as I said, I'm gonna upload the initial files which you can compare with to see which one works best for you for the result. Right? So I guess this is it for today. It's getting late. Again, I'm doing like 3.5 hours for now. Maybe I should just end the live at this point. Well, anyway, hopefully you liked it. Let me know if you have any comments or feedbacks. I'll be appreciated. I'll keep these as it is here. Okay. Let's call this. Oops. Let's call this solution 1. And I'm just gonna copy the one that I used before and bring it here to make it as a solution 2, shall we? So so that you can just compare those two. I don't really need those. Getting some errors here. What's with it? Fval. What is this? Okay. And reset the simulations and see if this is gonna work here. Yeah, still works. It's like the initial pass is already really not that bad, so it's giving you rather good result, rather better results than the first one. So maybe I'll just leave it here for your reference. Okay, well, the basic idea is pretty much the same. I'm just changing the way to sort. That's all. Okay, that's it. Hope you liked it. And as always, I'm going to upload the file to GitHub repository, and also at the Patreon you can download it for free. You can watch the archive for free later. I'll paste the link to the file after finishing the live stream. Okay. Alright, that's it. Thank you for joining. Thank you for listening till the end. Hopefully you got a bit of idea how I did it. And well, I'm sure it's a bit hard to follow some of the part because I did it a bit too quickly, so try to download the files and check what I've done. Alright, that's it. Night. And next week I am offline, so I'm not be able to do a live stream, so maybe 2 weeks from now I'm gonna do again some live stream. Okay, this is it. Thank you very much and good night.